We'll continue this village electrification example by looking at how we can specify the load and base case power system. So as part of specifying the load and base case power system, we're going to specify the costs of fuel and electricity. So in order to power the diesel genset, which is actually only used in the proposed case, we will specify that it costs 30 kwacha per liter delivered to the village. For electricity, which is purchased from the national grid in the base case, we're assuming 2 kwacha per kilowatt hour. So that's the cost of the utility to provide electricity. It does not include the cost of extending the grid to this village. Grid extension is going to cost about 500,000 kwacha per kilometer, and the village is about 35 kilometers from a point of interconnection, so it's going to be an expensive project to do grid extension. You may be surprised how expensive this is. I did a little bit of research on this, and people point out that often grid extension in a country like Zambia also implies additional load that requires building more capacity on the grid, or upgrading parts of the transmission or upstream distribution system. So perhaps 500,000 kwacha per kilometer is warranted. To maintain it, however, should be fairly inexpensive. I've assumed 20,000 kwacha per year, and to supply electricity, as we indicated earlier, it's 2 kwacha per kilowatt hour. The AC electricity requirement for both the base case and the proposed case. So there's no assumption that the load that the village generates will change depending on whether we have a PV battery genset system or the grid. That is an assumption that we might want to discuss if we were going to do this project. But for now, we're going to stick with that. The requirement is 600 kilowatt hours per day. The peak requirement is 150 kilowatt AC, and the system must provide power for 24 hours a day, 7 days a week. Of course, there can be minor downtimes, but the point here being that we cannot assume that the load is on only during the day, which would be beneficial for a PV system, or only during the night, which would be particularly difficult for the PV system to provide power for. So if you have a subscription, pause the video and attempt to continue with the analysis, and I will show you a solution momentarily. Alright, we'll go to the energy page and start with step 1 here, electricity and fuels. And here we can indicate that the only fuel that we're going to need, at least in this analysis, is going to be diesel. We know the price in terms of kwacha per liter. It's 30 kwacha per liter, so I will select liters as the units here and put in 30 as the fuel rate here. For the electricity rate, we will here put in the 2 kwacha per kilowatt hour. Having done that, we go to the power system and load characteristics. That's step 2. Here we're looking at the base case, a power system, as well as the load. The technology being used to provide power in the base case is grid extension, or grid electricity here. So the capacity is a gray cell, meaning we don't have to supply it if we don't wish to, but we'll just assume that the grid can supply at least 150 kilowatts of power, which is the peak electricity requirement. In reality, the grid would be able to supply much more than that, obviously. For the annual O&M costs, we have an assumption of 20,000 kwacha per year. Now we specify the load characteristics. There's no DC load, but in the base case and the proposed case, the load is assumed to be 600 kilowatt hours per day. And because the electricity needs to be supplied 24/7, we'll assume 0 intermittent resource load correlation. Arguably, we could pick negative here. That would then assume that all loads are on during the night. It would be a more conservative assumption in terms of the capabilities of the photovoltaic system. We're going to pick 0 here. For the peak load, we're going to enter 150 kilowatts here. The next step will be to specify the proposed case inverter and battery.